All right, good evening, everyone. Let's maybe get started a bit sooner than planned originally. We heard we have to be out of here by 9, so we want to leave you guys some time to network. So we'll get started with the talks a bit sooner. So thank you all for joining us tonight. We have a nice panel of speakers here. So Arne and Jules from ML6 are going to present, and then Kashif from Huggingface as well. So is the sound all right? Everybody can hear me fine? All right, nice. Yeah, so let's get started. Hope you enjoyed the pizza and drinks, and we'll have some time after the talk still for networking. Just first, a short introduction about ML6, as we're co-hosting this together with AI Camp. So ML6 is a company specialized in AI services, so we do mainly AI consulting. So we have 300 plus clients over the years, or 150 clients with 300 use cases. About 100 AI experts. We have several expertise domains that we focus in to develop knowledge, and we put a lot of time also in researching the latest AI trends. So yeah, we're mainly focused on delivering projects for clients on 3 different clouds, so GCP, Azure, AWS. We try to develop deep functional and domain expertise next to just like delivering the projects, so kind of taking clients end to end and not just body shopping projects. Next to that, we're also trying to focus a lot on being experts in both security and also ethical AI. So as said, we're specializing in several focus domains, trying to develop expertise in a very deep sector-specific way there. So looking at domains like AI in biology or energy, for example, generative AI as well, obviously. So we also try and develop codes and boilerplates to help us with that. Some of that we also open source. So you'll find this in GitHub as well. In general, we try and keep up with the latest tech stack and tools on the market. And also, share that and try and participate in the community by organizing events such as these. So as a company, we focus, as said, on delivering custom projects for clients, but also customized solutions with common platforms like our speakers today are going to present. And also we have Vandendorpe, which is an open source platform for data-centric processing. So you might have also seen this presented if you've joined any of our previous meetups. All right, so yeah, this is just like a selection of some companies we worked for. So different verticals like life sciences, healthcare, e-commerce, media technology, financial marketing, manufacturing, financial, many different sectors. And we're also regularly coming into the media attention with what we do. So we're one of the faster growing AI companies in the EU, according to the Financial Times. We've been nominated as Scale Up of the Year by Ernst & Young, some Google nominations and awards, and so on. And I'm also telling you this because we are looking for a lot of new colleagues this year. So we're trying to grow by almost 50%. So if you are interested in joining us, if this sounds interesting to you, you want to join our German office or maybe Belgian or Dutch even, please have a look at the job description page. So we're looking for data engineers, machine learning engineers, people, project managers, business development partners, a lot of different profiles. So feel free to apply or get in touch on LinkedIn with me. And now I'll leave the words to Ayana from AI Camp, who is also going to present AI Camp very shortly.
I will be quick. So I'm looking forward to the speakers. So I will be super quick. We are today from AI Camp. We are collaborating with ML6. So it's visible, yeah, okay. So I will tell you a bit who we are. So we are essentially a global community of around 300,000 AI developers and practitioners around the world. So we have, we organize basically and collaborate today with partners like ML6 around the world. So you could check us out. And we always looking for people to get involved. So we're looking for speakers, people to partners, sponsors, and event venues. here in Berlin. So if you guys know someone or interested to speak and present your project or anything that you work on for our next event, please contact us. And we held a lot of events like this one here, also online. If you go to our website, we have daily events, webinars and stuff that you can take part. And quick shout out that we always do, is anyone of you hiring here?
Yes.
Okay, yeah, so you guys could look into ML6. All right, and is there anyone who is working on a project that is looking for partners or collaborators? You can quickly tell a bit about your project and
realize basically I'm wanting to build a digital health startup, and I need someone who can help me on the technical aspect to either say it's not possible or it's possible and take it further. So I have a crazy idea, and so I'm looking for someone who's got experience in AI. So basically, yeah, that's it. My name's Dave.
so Dave here, who is you can guys go to him in case you can help. So thank you. Yes, that's good. Good to have an event like this. And you are here as well.
Yes, hi, I'm Andre from Autodesk. So we have our offices just down the hall on the left. If you're working on machine learning for 3D in any form or shape, please drop by and get in touch, because we're always looking for new people and we just filled most of our positions that we were looking for, but we're still looking for interns or collaborators and future positions. So we're just generally interested in meeting anybody who's working on 3D machine learning. Thanks.
Thank you. Anyone else? Or that's it? Okay. I think that's it. So as I said, here a bit of who our partners were in the past, our clients and sponsors. And today, big thank you to ML6 and the Merentix campus for the venue. And again, I would not want to take more of your time. So let's begin with the first speaker. Thank you.
All right, so now we give the floor to Kashif for his talk on RLHF.
Thank you.
Is that? Oh my God. Yeah, to share my screen or what? Share.
Share.
Tab. Share. Is that work?
Yeah, I think actually also
What does that mean?
so you can just exit the call and go back.
Exit?
Yeah. You can join us, rejoin, and you can find your notes, start below that. Yeah, and that just shows your screen share, not your webcam. And you can just share your screen as full screen for everyone. All right.
Is that better?
Thanks. Yeah.
All right, so yes, thank you so much. I'm Kashif from Huggingface. I wanted to talk about direct preference optimization for LLMs, which is a kind of a new RLHF technique. And, we expect LLMs to be useful, and there's somehow are, but they also have a lot of problems from, getting up-to-date information and generating appropriate responses. And so this talk hopefully is a solution to Yeah, so a solution to appropriate responses is offered by alignment. Alignment is just the process of encoding human values and goals into LLMs. And through alignment, one can tailor these LLM models to follow, say, business rules or policies. And so let me highlight here why one would need alignment. So if you, I mean, I guess the big issue is that if you take a pre-trained base model that's been trained just, on predicting the next token over some large corpus of data, then typically, you can think of such models as autocompleters on steroids. And so they may not necessarily answer some typical question you're interested in. So in this kind of toy example, where you're asking about whether pineapple on pizza is a crime, the autocompleter, the model will just spit out some text unrelated to the question, mostly because of what it's been trained on, and so it's not really useful at this stage. And what's typically done is this idea of kind of supervised fine-tuning. So if, for example, you require question answering LLM, then you can train it on specific human or synthetic questions and answers in some appropriate manner. But here again, after doing supervised fine-tuning, the model will spit out potentially biased or inappropriate answers based on the tokens in the prompt and completions that are in the training data. So perhaps the human annotator that answered this question really hated pineapples on pizza, or the word token, occurred much more when talking about serious matters. And so the fine-tuned model will express these human or annotator biases. And so if you were a pizza company, such a chatbot would not be appropriate. So alignment offers a way to move the LLMs closer to the preferences of humans by essentially training the model on data of completions that have been judged either to be good or bad using, again, human or machine learning annotators. So at a high level, we are essentially trying to teach the model that the preferred responses shown here with thumbs up should be generated much more often, and those responses that we deem with the thumb down should never be generated, or generated less often given such a prompt. So that's our goal. And so once trains an aligned model, as you probably know from the popularity of ChatGPT or Claude and all these other models, are much more human-like and potentially useful, especially for some specific tasks like summarization and so forth. And alignment is typically thought of, maybe you think of alignment perhaps as like censoring the model, but in reality it's much more than that. We as a collective have certain culture or tradition and would like the LLM to mimic those, and so neural networks can be trained to align with these specific traits or norms, which we would like in our answers. Please stop me if you have questions. So the original approach from OpenAI was called RLHF, and it's a multi-step approach. The first approach, of course, the first step, of course, is to take data from human annotators of high quality questions and answers, and then fine-tune a bunch of GPT models on that data. Back when this paper came up, there weren't many open source data sets. That situation has changed, and so just as an aside, if you wanted to do that yourself, there's a whole bunch of high quality data sets available these days. So you can also follow this recipe if you want. The next step, what OpenAI did was to take a chat model and try to model human preferences. And so they took a collection of prompts and got a variety of responses from their chat model, and these answers were then rated by human annotators from best to worst. And then a new type of model called a reward model was cooked up as a regression task from these labels to mimic the preferences of the human annotators. And at inference time, this reward model will give you a score for the response given some prompt. And then these scores can be used as a proxy for those human annotators. So again, just wanted to say that now we have many public, good, bad, or good responses, bad responses data sets as well. So if you wanted to train your own reward model, that's also now possible as well. High quality reward models. So back to RLHF, now we have a chat model, we have a reward model, and the final step is to combine these two to create a new chat model that has learned to encode the signal from the reward model. And the way OpenAI did it was to use the machinery of reinforcement learning. And so the basic idea is that you're given a prompt, the model outputs something, and then the reward model can be used as a signal to nudge the weights of the model so that the model outputs more responses that have a higher reward and less often responses that have a low reward. And the result of doing this at scale is essentially ChatGPT or Anthropic's Claude chat models. Questions? Yeah. Yes.
You don't need to repeat the same process for million different queries. That's the benefit.
Essentially,
Yeah.
yes, because of the reward model.
Okay.
And would you say if there is a project, like a real project for a company that wants to replay or like have help for their, for example, call center managers, that the chat replies to people, would it be the same? Like, would it follow implementation the same steps that you have step 1, step 2, where you have, for example, agents from the call center who evaluate possible answers and then they rate them? Would that be the way to implement it?
In some sense, yes. So, of course, when you have such data, then you can use it to augment your model to follow those. And RLHF and the machinery of this recipe is one way of doing that, of course. Mathematically, I guess the idea is that we're trying to maximize the reward that the model can get, meaning you give it these prompts and the reward model gives you a score, and then is my, let's see. Yeah, so then I guess the essence is that you want to maximize, you want to nudge your model so that this reward is maximized. And if only this part was in your loss, then what happens is that a concept called reward hacking, meaning that the chat model can learn that if it outputs some quirk or some special token, it gets very high reward, because the reward model is also not perfect. And so what OpenAI did was they added this extra term here. This is an extra term essentially needs a reference model and essentially penalizes the weights of the original model to not go too far away from the reward model, so that at least it continues to be a good chat model, even if it's learning to generate good responses with high reward. The issue here is, well, anyone who's done RL reinforcement learning will know that doing this is very finicky. It's tricky, and there's a nice blog post about all the kind of the implementation details that matter when you're trying to implement such a thing. The other big issue is that now you have essentially 3 large language models that you're juggling in your final loss, and so trying to do that at scale, it becomes a kind of more engineering issue than a scientific one. So the idea behind direct preference optimization, the topic of this talk, is to say that perhaps we don't need RL. Without RL, the authors of this paper ask what other alternatives are there. And the main observations they make is that the model itself that you're trying to optimize can be used as a proxy for the reward model. So one uses the original chat language model, and through the process of optimization learns to model the good or bad preferences directly in this kind of a less complicated loss, in the sense that now you only have the main model and a reference model. And this loss is kind of a supervised, can be done in a supervised fashion. So let's pick apart that loss a little bit. So at a very high level, this DPO objective is that we take good and bad responses to a given prompt X. So X is our prompt, like is pineapple on pizza a crime? And then you have a good response and a bad one. And this tuple becomes your data set. So essentially you sample such tuples from your data set and try to maximize this reward. So given that we're going to compute, given this tuple, we're going to compute two things. Basically, the log probability that the model is able to predict the chosen response as a ratio, where the bottom, this bottom thing is the log probability with respect to the reference model. So essentially, what you want is what you're pushing the model to do is is pushing it to generate the chosen response. But because of this ratio, you're also kind of constraining it not to go too far away from the reference model, essentially doing the task of the second term in the original RLHF objective. And then the second term is essentially the same one with respect to the unpreferred log probability and the unpreferred log probability with respect to the reference model. And so these two terms are stuck together with the beta hyperparameter and the negative sign. So essentially this, if your model predicts the bad responses much more often, this thing, because it's in a sigmoid, is going to be large, and you're going to get punished much more than if this part was bigger than the other one. So in this way, you're essentially, with this weighting, you're essentially pushing the model to generate good and bad responses, to generate better good responses and stay away from the bad ones. And this is really simple. Once all the tensors have been prepared, this loss is essentially 10 lines of code. The beta hyperparameter also has an effect. Essentially, what the model is doing is trying to create a margin between the good responses and the bad ones. And this beta hyperparameter kind of controls how far away you want your responses, the good ones and the bad ones, to be. So this is somewhat important as an implementation detail, because if your data, it might not be perfect. And so if your data is not perfect, then you maybe want a smaller beta so that you don't push the good ones, the potentially good responses too far into the bad part of the loss. You can also think of it as in another way, in a funny way. Without all the maths, you essentially are doing gradient descent on the good stuff and gradient ascent on the bad stuff. So you're kind of, essentially that's what's going on here. Yes?
Like a more general, like the tests I did, like when I have like the base model, I get like more like powerful answer, I would say. But the more you just fine tune it on alignment, the more generic answers you get. So like there was like this.
No, it's the other way around. The base model is the one that's generic. And
Yeah,
typically the base model is the original model without, before doing any alignment.
Yeah, what I wanted to say is like, remember when the March, the GPT-4 model came out, was like, and the more they do like the alignment and so on, the less powerful kind of it gets.
Right, right.
It's like more,
So that, in some sense, of course, is the preference tuning. You know, you're pushing the weights to some preferences, and those preferences might not be like very general. So it does have that effect, of course. Okay. If you want to do that yourself now, there's essentially two main libraries to do this, namely TRL from Huggingface and Axolot as well, which the community has been using. And using these ideas and data sets, the community has also cooked up a bunch of very powerful or very performant open chat models as well. And here's a few examples of them as well. Actually, everything in the slide that is links are clickable. So once you have the PDF, you can go to those references. Yes.
So these are different reward models, or what are?
No, there is no reward model anymore. There's just the reference model as well as just the main model.
No, in the next slide you reference
Which one?
the next slide. Yeah. What are these then?
These are the final models after doing preference tuning on open data sets of good and bad preferences.
Okay.
Trained using that DPO supervised loss without the complicated machinery of reinforcement learning. That requires not only a reference model, but also a powerful reward model.
Two questions.
Yes.
Yeah. One of them is that.
Where are you?
Yeah.
Ah, yeah.
Yeah. I think different kind of coefficients to the loss function could potentially mean that the answers we are gonna get is better suited for the end result. But how
Right.
much effect do they have on a convergence results?
Convergence.
How much more overload in the computational resources will we have? I
Right.
think. And second
So
question, maybe if this is long, we can take it offline. Second
no.
question is
Yeah.
that as a human, we are not interested in a single discrete answers like yes or no.
Yes.
So building like a big data sets of yes or no might be currently effective.
Mhm.
But the thing is that as a human, we are interested in a like long chain of
Of
sources
course.
from like one answer to another.
Sure.
Everything could potentially change. So is
Right.
there any measure of this divergence between how humans are making this chains and versus LLMs making this chains, and how long they can follow the human thinking?
Well, okay. So for the first one,
Got
of
it.
course, the first question, the computational resources twice as much. So you need to juggle just two models with DPO versus three large models. And in the RL world, you also have to then in each loop also have to do sampling. And then you sample and then you have the reward model, then you give scores. Here there's just your data and the reference model, which is you just use it in the forward pass, and the main model. And so it's, let's say, you know, two-thirds of the computational and memory requirements of PPO.
So second question.
Second question, the yes and no business was just as an example, just to fit on the slide. Typically, the answers are nuanced and complicated, and different annotators might give different answers to or different preferences to the answers. And so I don't know how to judge it after that with respect to, I mean, so I'll talk about evaluations at the end. So there are also evaluations. Maybe I can talk about that at the end. Just to wrap up this first part, I just wanted to say, just like in other areas of machine learning, when some new idea comes up, people start cooking up variations of it or try to make it better. And the same has happened here as well with methods like IPO, KTO, and iterative DPO as well. Two ones I wanted to highlight are KTO. In KTO, they do away with the data that is like a prompt and a related yes or no. Well, instead, they have just a prompt and completion, which is good, and some other unrelated prompt and completion, which is bad. And so those two don't have to be related. And you can cook up a similar loss to DPO via that. And so this kind of data is much more readily available than kind of binarized yes or no data. Okay. Okay. So the second part is much more practical. Essentially wanted to show you how to run and fine tune these preference optimizations algorithms on your own data set with details on especially how to format the data in order to tokenize it. Then I'll touch upon metrics and evaluation as well. And some, if he lets me, some things to watch out when you're training. So also there in the slides, there's also collab notebooks as well, and some blog posts, especially with respect to training on in a efficient manner, using techniques like LoRa and DORA. And in fact, the person who implemented these in Huggingface is also here somewhere. Yeah, he's sitting there in the back. So do talk to him if you're interested in that. So the first step, of course, as I said, is always to do the supervised fine tuning for chat models, and that typically involves finding a data set. And in this example, it's called the Ultra Chat data set that contains 2 splits, and each row, each entity contains a prompt and a message, the response. So here's an example of the prompts, and in this data set, it's things like which famous landmarks to visit, and recipes. And these answers can be like a single turn, just one response, or it can also be multi-turn, where the person is asking the chatbot, in multiple turns. Do I have a picture of that? So again, if you're interested in such data set, there's also a collection of these data sets here. So you can have a look at those via the link in the PDF if you ever get that. So when you have messages in a data set, you really need to format them in a specific way for the model to perform, in order to perform fine tuning. And this is done via something called chat templates. There are a number of examples of different chat templates, like chat ML, Llama 2, and so forth. So what this essentially is that that you have like a sequence of messages that have been asked to a chatbot, and these need to be formatted for the model to then fine tune. And so the idea is that one can delineate different sections of this back and forth conversation via different tokens. So in this example, there's something called a system token. In this case, it's empty, and after that, you have the user token, the assistant token, and so forth. Just let me dwell very quickly on the system token here. It's blank in this case, in this content, but there can be stuff in here as well. And what is typically in there is essentially a way of giving your chat model some kind of personality. So for example, if you want your chat model to talk like a pirate, you would prompt it via that system token. Some data sets contain system tokens, contain stuff in there that then helps to explain the conversation, and other times it's empty. There's, as I said, there's a number of templates, but we typically recommend people to use the chat ML one, which is somehow the most suitable one. To apply a chat template is super simple as well via the latest transformers library. You just define a Jinja string that templates your message, and then you can just call tokenizer with apply chat template to your message, and it'll format it appropriately. Right. That's the Jinja template. Once the data is formatted via the chat template, to run supervised fine-tuning is again quite simple with the transformers TRL library. You just load up the TRL, initialize some training arguments, and then initialize your supervised fine-tuning trainer with the appropriate training and evaluation datasets that have been mapped via the chat template. And then just call train on it. And just if you wait for this a couple of hours, you should have a supervised fine-tune checkpoint saved for you. Once you have this SFT model, you need to perform alignment for some particular use case. And in terms of the steps, it's again very similar to, if you're doing DPO, very similar to the SFT. So the main difference with preference data is that, together with the prompts, one now has chosen and rejected, which are your human and AI annotated to chosen and rejected binary examples. Yeah. And again, there's a nice collection of data sets on the hub, which contain such binarized responses. So as I said, these messages contain a prompt and a chosen and rejected response, like you see here. But if you look at the loss from earlier, the tuple X corresponds to the prompt here, and then the chosen and the rejected correspond, as I said, to the one with the underscore winning and the losing response in the DPO loss. And not all datasets have such a binarized component. As I said, it's much easier to have ranked responses. And there are datasets with such ranked responses. In this example, there's 4 of them, where typically rank 1 is my time up.
We have 10 more minutes or so.
Huh?
10 more minutes or so.
Yeah, okay. 10 more minutes. And so if you have such a data set, you can convert it into a binarized data set by setting the preference data, the best one as your chosen. And then you can, for example, randomly choose between these, the other ones as your unpreferred response. When you have multi-turn data set as well, it's typically the last response that differs. So in terms of applying now the chat template, essentially those chosen and rejected responses are independent, and it's only in the loss where they're kind of mixed. So in your batch, you would have these as independent, batch indices, and only in the loss is where something goes on between. So for DPO, this is typically, as I said, the very last one is chosen or rejected. And this is how you typically apply that chat template to your binarized data set that has a prompt chosen and rejected key. So the DPO trainer in TRL can be used just like the self-supervised trainer, supervised fine-tuning trainer. You give it the model that you wish to train, and in this case, the trainer can also take a reference model. But if you don't give it one, it'll use that one, a frozen version of that as your reference model. And again, you can define the DPO trainer exactly like the self-supervised fine-tuning trainer, and just call train on it. With, of course, the beta hyperparameter, the appropriate beta hyperparameter, which you have to figure out which one is the best for you. Right? And we also have a blog post about the effect of this beta parameter on downstream evaluations as well, if you're interested. Some tips when you go and run these algorithms are highlighted here. Of course, the beta itself needs to be tested. The advice is typically to test the very small betas more often. So you want to test, smaller ones more often than the larger ones. The learning rate also has to be much smaller, like a couple of orders of magnitude smaller. The batch size needs to be large, so as large as your GPU can handle. The optimization method is an interesting question. The original paper was using RMS prop, but we find that Adam also performs better. In terms of the learning rate scheduler, the cosine we found to be the best. Another interesting observation is that if you take your best supervised fine-tuning model and then you perform DPU on it, then it will not give you the best DPO model. Sometimes the worst performing supervised fine-tuning model will give a better DPO model on the same data set. So it's really worth going over your whole SFT plus DPO pipeline as a single entity and then do hyperparameter tuning on that rather than the separate SFT and DPO. Some observations with LoRa, again, is which is the preference, which is the efficient fine-tuning library that Benjamin is developing, is that it appears that LoRa is a kind of a regularizer, and the models trained with LoRa tend to overfit less than if you were doing full fine-tuning. Okay, maybe I'll stop here.
Thank you.
For questions. We have time for questions? Yes. Questions.
Hi, thank you for
Hello.
the talk. I have one question about the loss function calculation. So it matters if we use maybe the prompt complete and not just the response when we are doing supervised fine tuning, or this is?
Supervised fine-tuning?
Yeah. So because sometimes we have prompts and the completion, and we
Yes.
calculate the loss in the full.
No,
like
there's
a
typically
input
with
or just the
supervised
response?
fine-tuning, yeah, it's done for the completion part.
Okay.
Yeah, so it's for supervised fine-tuning, it's just this loss, the negative log likelihood, essentially. Where this, of course, there's no concept of good or bad. It's just this part here.
Okay.
Yeah.
And we use only the token that are part of the responsive, but not the token.
Exactly. Because that part of like next token generation has already been done by the pre-trained language model. So typically you're doing that, if I'm not mistaken.
Okay, thank you very much.
And when you implement the model and you want to iterate, like improve it in the future, you
Yes.
collect some analytics, right? Like what do you use to collect analytics, some metrics on the performance, on the responses, like
right.
which library?
So
do
once
use?
you have the PDF, typically you can use MTBench and Alpaca Eval to evaluate the final model. These libraries come with a set of questions and answers, and then the responses are judged by GPT-4 typically, and then that kind of gives you a kind of gives you a good metric to compare your performance of your model. The other nice thing here is this benchmark correlation, where they kind of correlated all the different LLM benchmarks. And they found out one interesting thing is that this empty bench is highly correlated with human responses. And so it's a good proxy. It's a good proxy for human evaluation, this empty bench.
Okay, thank you.
No worries. There was another question in the back.
Last two questions, maybe.
Thank you. So one question, if you want to add more knowledge to this network, basically extend pre-training later, can you do this after all these SFT and
I believe so.
PPO?
I think adding knowledge is kind of somewhat orthogonal to this business. You know, essentially, at inference time, you're just you're sampling from some distribution rather than extracting knowledge. But yeah, I suppose you can do it after, but you know, the way stochastic gradient descent works, it's no guarantee that, you know, training something afterwards will somehow be much more prevalent when it does a generation. I don't know.
Okay, thank you.
Yeah, so there's other ways of doing that. I guess the ML6 people will know all about that.
Hi, I have a question about, I think it's about system prompting.
Right.
And because most LLMs are like you ask a question and it answers, but how would you do it if you want the LLM to ask a question? Would it be only system prompting or so? Do you understand what I?
Yeah, I think so. Okay. So it starts like a psychologist. It starts asking.
Yeah.
I don't know, Benjamin. I don't know.
Isn't it very important? I mean, for the whole.
I guess if you, yeah, you could train it with some token to start or prompt it that prompt it to say, you know, you should start generating some questions because I'm a patient or something.
Yeah,
And
or maybe you say like hi, and then it starts. Asking.
Right,
So
you can
give
prompt
the
it.
first
Yeah,
thing
okay.
and-
Yeah,
Would it?
that's a
be-
good idea.
Yeah.
That
But
could
would
work.
it go via system prompting or?
No, just put it
No?
in before in the user interface, right?
Okay,
Hide it,
okay, okay.
for example.
Right, I think that's all the time we have. So
No
thank you again to
worries.
the speaker.
Yeah.
And then now Arne, my colleague, is going to join us for a talk on 3D vision learning.
Oh
I
my
believe.
God.
All right.
Is this the last one?
No, that didn't be the last one. I don't know, is this? Thank you. Bye. Success. Thanks.
All right. So tough act to follow, but I'll try. So today, I already heard a request for 3D computer vision engineers, so that's nice. Indeed, I am from ML6. I'm a computer vision engineer, and today, especially in light of like recent developments like Gaussian splatting or semi-recent, seeing as the mountain of follow-up papers is growing quickly, I would like to take a look at how we, as ML6, and also wider, look at how we incorporate that into our projects and where we think it's going. So for me, I have a focus on computer vision, and then I have a sub-focus. So I'm also active in the niche of manufacturing. So what does that mean? That's a lot of computer vision on conveyor belts, spotting, anomaly spotting, defects, also a lot of robots, manipulation, and so 3D also comes into play there. It's not only manufacturing though. You see one case where it's a bit of sport analytics, but it's all around computer vision and then a niche in manufacturing. who I am not. I am not an expert in Blender, Unity, graphics design, and so on. So if you ask me a lot of questions about those, I will try to answer, but probably not spectacularly well. Right, that being said, on the agenda. So a perfect storm hitting the world of computer 3D vision. That's where we'll start off. Then also, again, how do we look at it in our real-world projects? And then finally, we'll get to the actual meat of this presentation and take a look at Gaussian splatting and its role in 3D reconstruction, synthetic data, and so on. Right, so why is a perfect storm hitting the world of 3D vision? Well, actually, the inspiration for this subject and my enthusiasm for it came a bit randomly, as things do through Twitter as well. So on the left, maybe some of you have seen it. Oh, on X, I should say. So a post where we see a Gaussian splat of a Nike shoe. Maybe first, before we go, for who is Gaussian splatting totally new? Okay, see one, nice. All right, great. So I have some useful things to say to at least a part of the group. Right, so I think what astonished me mostly here is the level of detail that we are seeing, especially if you look at the see-through fiber in there. And then reading a bit further on the creation of it, knowing that this is not a rendered video, but actually, or not a pre-rendered video, but actually a real-time render. That really blew my mind personally and opened up a lot of possibilities. And then on the right, also very interesting. So OpenAI's Sora release, so text to video, was already pretty impressive. But then I saw someone actually using Gaussian splats to create a 3D reconstruction of it. So Sora actually seems to output temporally consistent video that can then be constructed and splatted. So again, the enthusiasm for the subject was rising. And then next to that, on the right, so the Apple Vision Pro, obviously, again, rekindling the AR, VR hype a bit. And then on the left, some foundation models like depth anything. So monocular vision to depth maps, really opening up a lot of possibilities. And then, because as I said, I'm a practical guy, we do practical projects. In the back of my mind, I remember the GOAT himself when he was still at Tesla AI. And this article in Forbes where he said they were dropping LiDAR from the fleet because he said vision is necessary to the tasks of self-driving, and it should be sufficient as well. And if it's sufficient, then the extra hassle of dealing with the sensors, the data merging, the wrangling, it's not worth it, right? And so from that, I took human eyeballs are all you need in a lot of cases. And so because humans do infer the depth, they do use the information and the world priors they have from stereo vision. But humans do not measure depth, right? So there are some limitations to the whole thing. So that again is a bit the intro, the reason that we as ML6 started looking, how do we keep going forward with 3D data? How do we tackle it in our projects? So in those projects then, a very simple or simplistic representation of the classical steps. So we capture the data, pre-process, model inference, post-processing and outputs. And again, practical as we are, what do we do in the model inference? What do we train the model to do? What do we capture data for? And what are we going to fix in post? Always an important trade-off. Especially so for 3D data, because 3D data, a lot harder to get by, harder to label, and so on. So our approach has mostly been, let's do as much as we can in post-processing. So the very simple example I put here, assume we're counting sheep. We could train a model, a regression model to just take an input image and output the number of sheep in an image. That will probably work given enough data. But I think everyone in this room would just use an object detector probably off the shelf, and then just count the number of outputs. So again, let's do things in post as long as it makes sense. And then we also had the observation, playing a bit around with the models. This is already from a while ago. We also output a blog post back then where we tested, among others, 3Detter, PointNet, and so on. And where we see they do exist, but the adoption is a bit limited, hard to fine tune. You need to have the data and so on. So again, we kept doing most things in post as far as we could. And then the second observation as well. So it's again, the necessity for the 3D data, seeing as human eyeballs are often what we need the most and the only thing we need, that the necessity came from the post-processing step itself and the output. So either in post-processing to make the decision we needed to measure, and so that is really an exact and a sensor thing, or the output just needs to be in a 3D modality if we're steering robots, if we need to visualize something in 3D. And so it really went a bit beyond the model inference. And so again, we kept doing things in post. And then this was our approach for most of those projects. So indeed, we did have our 2D image captures. We did have our 3D image captures. We merged them during pre-processing. We do most of our inference in 2D, and then again, the 3D data enters later. Now though, seeing that Gaussian splatting is getting better, seeing that 3D reconstruction is getting easier, again, thinking about the Tesla example, we might be able to start dropping our 3D sensors and simply reconstructing from the 2D and then go from there. Again, leveraging the large base of existing open source 2D foundation models and so on. So, a very long introduction to finally get to 3D Gaussian splatting. Some more introduction. So, 3D reconstruction, what are we doing? So from a set of input images, we want to, reconstruct the underlying geometry and also generate novel views then from it. So the input data would then be so separate images with some overlap in there. And we want to extract a point cloud. So for the underlying geometry, typically structure from motion, algorithms like Colmop and so on. And then the multi-view synthesis, so coming from the point clouds and the input images we have, how do we construct these novel views from multiple viewpoints? 3 different flavors. So typically, or the most, the oldest one is estimating a mesh, texturizing the mesh, and then working with the mesh directly. Also, this is again what is most typically done in animation, so working in Unity, working in Blender, and so on, where I'm not an expert on. Then 2020, neural radiant fields entered the field. And then very recently now, 2023, we had 3D Gaussian splatting. So this was in August 2023. But important here, in the purest form, all 3 they start from the same input. So having that, or taking structure from motion, having that point cloud, having those camera positions, and then going on to reconstruct the scene. So, so the mesh estimation, typically geometrically accurate, and I'll see a counterexample of what I mean by that in a second. And again, plays nice with all of the existing animation tools out there. So for gaming, for videographers, and so on. But a lot of images, because we really need an input of what we want to represent. Again, the novel view generation, not as straightforward here. It does not generate novel views. And also the reflective surfaces and all of the good stuff, those have to be added on top later. They don't come really ingrained in the methods. But then, interesting, nerves. So what is a nerve? Essentially what we're going to do here is take our input point cloud, take our priors, and then train a model to really encompass the entire scene, right? So the model has to be a representation of the scene. We really want to overfit our model intentional on one scene. And so then rendering that scene is actually inferencing the model for a specific point in 3D space, which has some very nice visual properties. So again, these nice reflective surfaces that we have, the high visual fidelity, but the downside, so again, not necessarily geometrically accurate here, slow training process, and this is the big one, very compute-intensive inference as well. So real-time inference is not really a thing when we're dealing with nerves. Well, in most cases, especially if we do want that high visual fidelity. And again, animating these nerves, not as straightforward. We need plugins to then import them into Blender, Unity, and so on. But then, no, not then yet. So a quick note on the not necessarily geometrically accurate. So on the right, you see a render video of a nerve where we actually go through a mirror. So these nerves are really just trained to optimize for like the visual quality. So there is such a thing as a mirror world in nerves. So thinking about practical projects, if we're going to measure based on nerves, that will be a problem, seeing as extreme examples as these can happen. Then 3D Gaussian splatting enters the scene. And so first, what are we doing? We're not doing things like in nerves where we're going to fit a neural network to represent a scene. We're not training a network, but we are using gradient descent. So the same training step is implied. And what we're starting from is, again, our point cloud. And then just for comparison, I put a 2D Gaussian on the screen here as well, to make the simple step then to a 3D Gaussian. And so each 3D Gaussian, of course, has a position, covariance matrix, color, and an alpha, which is the transparency of it. If we then project or rasterize the Gaussian into 2D, we can see it as its color that is fading out towards its edges. And again, superposing these projected Gaussians then allows us to make really complex images. And so indeed, the fitting of these Gaussians to the different views that we have of a scene, this is the training step. If we do this for enough Gaussians, say 7 million, we get what we want. We get an accurate representation of a scene, able to capture a lot of detail, but with the added benefit that to render it now, we don't have to inference a model. What we have to do is, again, rasterize, so project the Gaussians, superpose them front to back, and we get a very, very efficient rendering engine, basically. Which then could look something like this on one of the classic data sets of the field. Now, important here also is just to see the Gaussian splatting as a new data format, a representation of the scene that is very efficient to, or more efficient to train, as well as to render, and so will allow us to speed up everything around it. And before I get to that point, I still have another slide here going over the advantages, disadvantages, and also an example, just a toy example of one of my colleagues' dog, where we take one image and try to represent it as the Gaussian. You can very clearly see the process fitting the Gaussians. So it's not even, I didn't let it run until the entire end, and you can still see some Gaussians, which are like very broad strokes in there. So imagine this happening from multiple viewpoints, and we get to our high visual fidelity image, very fast training times, very fast real-time rendering. But again, with the same issues, they are not meshes, they're not texturized meshes. Thus, so to really animate them, we need some extra conversion step. We need extra plugins again. But then, and this is maybe even the most important point, is that having this very efficient data format as well has triggered an avalanche of follow-up research that are all very nicely represented here in this repository. I definitely would advise to take a look. And there are two that I put here as well. So the segment anything model on 2D images released by FAIR, so Meta Research, somewhere last year. Also has its 3D variant now here using 3D Gaussian. So again, using the data format. Then on the right, same thing. So Langsplat really using the format to go and embed textual features in that 3D space. With nerves, this is also possible, but again, the really long inference times make the whole process slower, stifle iterations, and so on. And I think that's one of the most exciting things about this breakthrough. So those were just two I highlighted, and that already brings me to the end. I hope I've inspired at least some who hadn't heard about Gaussian splatting to take a look at it. I'm very excited to see where it goes, and I'll happily take some questions.
So if you could explain about the, like, how do you process the ground truth? Like, I was really confused when you talked about point cloud as an input to the model.
Mm-hmm. Yeah.
So what is exactly our ground truth? And if only point cloud is being projected in a Gaussian space, how do we make up for the semantic density of an RGB image? So that's where I got a little confused.
Yes. And so semantic density, we're not talking about any of the textual embeddings here yet, right? Or are the... okay, so then indeed, what is the ground truth and what is the starting point maybe? So we start from the point clouds where each Gaussian starts as centered on one of these point clouds that we have extracted from the structure from motion approach. And so then the optimization process really takes a look at the ground truth images we have from the scene and tries to optimize the Gaussians in that projection for that view. And so given enough views, we get this 3D accurate representation of it, if that makes answers your question.
So it's like a camera and a LiDAR mounted together and capturing the scene from different perspectives?
No, not entirely, because so what we assume to start the fitting of the Gaussians with is already on one hand the point clouds, so having the actual points in space of the scene in combination with the camera poses. So a structure from motion gives us both. And so we know that looking at the scene from this camera pose, we should have this image. And so that then represents our ground truth that we can optimize that specific image for.
Okay, yeah, that answers my question. Thank you.
Thanks for the presentation. Super interesting. I wanted to ask about the texturing in the Gaussian splatting. The textures and the bike data set looks super nice. Like, is it able? You say it's generalized to novel views, but how does it work with the texturing? Is it able to generalize also in terms of where the shades are going to be, or is it a parameter that you can also learn to use in inference?
So a bit different from nerves. So we are, if we take a step back and take a look at nerves, nerves are really ray tracers essentially. So rays are cast through the scene, and the models samples along the ray and returns what is there. And so naturally with that approach, it is better able to capture the different shading, the lighting, and so on because of that ray tracing characteristic. Gaussian splatting being a rasterizer, so a projector of the Gaussians and then just a superposer of those Gaussians, does not have that mechanism baked in. However, it does pick up on the shade and the lighting that is in the input images as well, to really get to play with the lighting afterwards. Again, things have to be added on top of the Gaussian splat, just like the texturized mesh model would as well. But so it does capture it to some degree, but not as natively as these very high quality nerves would in this case.
Okay.
I was just curious what you think makes the big impact here with the Gaussians compared to the nerves. So what kind of applications does it allow that nerves don't yet? Like I mean, one is of course performance, right? But are there other like differences in principle for this?
Yeah, it's a very interesting question. I think, so again, you mentioned performance, the big one. But then again, Google has also released a Smurf pretty recently, which also very high quality and fast rendering time, still a very long training time. But what I do think personally is that the fact that we're not dealing with a neural network, but a data structure that is more explainable to some degree, yet differentiable. I think that is the, but this is more from a research perspective. Again, as a practical person, we don't, I can't go too deep into that, but I think, or I feel like that would be another big one for me.
Great. No more questions? Let's thank the speaker again. Now, for the final talk of the evening, we have Jules talking about multimodality.
Yes, all right. Final talk of the day. And the goal of this talk is to convince you that there's more than words and it's time to get multimodal. Of course, I'll explain what I mean by that. So first of all, I'm going to start with an introduction just to set the scene. What do I mean when I talk about multiple modalities, multimodal models? I think most people here probably know it, but just setting the scene. Then next, I will dive into two types of categories of models that I consider multimodal. First one being open world object detection. And then the second one, which is the true interesting one, is the multimodal LLMs or large multimodal models, LMMs. And then of course, I'll end with a conclusion and some next steps and things you can take away after the talk. So diving straight in. So just again, setting the scene, when I talk about multimodal models, it's a model that takes as input multiple modalities. Typically, we talk about this in the sense of large models. I think everyone knows LLMs, chat models like ChatGPT. Even people that are not familiar with AI have heard about ChatGPT. And other types of models as well. It has been like this big influence. A lot of things became possible, but like Arne, I'm a computer vision guy, so I didn't really get that excited because it was still NLP. It was still text. Of course, it was cool, but didn't excite me that much. For me, it got really interesting when we had these other modalities that could be used as input. And of course, these days, we can feed into these large models, text, structured data, images, and even audio. But for today specifically, I'm going to dive into models that take a combination of two modalities being text and images. So as soon as images got involved, that's when for me it also got interesting as a computer vision person. So these first categories, some people might disagree that this is a multimodal model. I mean, in the theoretical sense, it takes in multiple modalities, but it's not really a large model. But I do want to mention it anyway, because in my opinion, this is a bit where it all started. So this first group are the open world object detectors. So just a very quick overview what these types of models are. So again, as I said, take both text and images as input, so multimodal. But the text is basically a list of the things you want to detect. So open world object detectors, open vocabulary object detectors, they're not trained on a specific set of classes that they detect. You can feed in the things that you want to detect, and then you'll make it happen. So you feed in your input vocabulary, that goes through a text encoder, you get text embeddings. Then on the other side, you feed in an image that goes through like a typical image backbone, which extracts image features. Then depending on the specific model that you use, I've just called it the vision language interaction. Some magic happens combining the two. And then there's region text matching. And as an end result, you basically get bounding boxes of these things that you want to detect. So this doesn't sound that exciting because this is a very simple example. You feed in man, woman, dog, and you detect those things. Not rocket science at all. But what's interesting, for example, with YOLO World, which was recently released, it has some reasoning capability. So instead of just saying, I want to detect a person, a dog, you can actually say, okay, I want to detect the person in red. And it will actually only give you a bounding box for the person in red, or the brown animal, or the tallest person. So as you can see, it's not just simply trained on what a person is, what a dog is, whatever object is. There is some sense of reasoning already. And again, the reason I mention it, because for me, this is where it started. Like, this was the first look into a world where I have a use case, I want to detect X in an image. And a couple of years ago, we would say, okay, let's start gathering a data set, start annotating, train it, and it's done. This was the first look into a world where basically we would no longer have to do that, because I just feed in whatever I want to detect into these types of models, and I can detect it. So that was pretty cool, but unfortunately, we're not there yet. So YOLO World being one of the more recent ones, I experimented with it myself. Some simple examples. I feed in this, for me, very simple image of a bunch of potatoes, and it has very low confidence threshold predictions for potatoes, and it misses a lot of them, which to me was like a simple case, but clearly to me this shows, okay, it's promising, but we're not there yet. Another example here, very common objects, like it detects the person on the side here, but here the person on the bike, which to me is the more obvious person in the image, was not detected, even after playing with the thresholds a little bit. So yeah, clearly interesting models, but yeah, not there yet. So as a quick summary for those types of models, if anyone's interested, are there actual use cases for these types of models? Yes, these models are quite fast. They can work in real time. For example, the YOLO World model can do real-time object detection on an open vocabulary. So that's interesting. And of course, you get bounding boxes. If you have a use case where you need bounding boxes, that's nice. But as I've just shown, limited recall, limited accuracy, it's not that great. And the reasoning capabilities that it has are rather limited. So when should you use these types of models? When you want to detect common objects, very important, common objects at near real-time speeds, and you don't have data to train something custom. And of course, if you don't require great accuracy. If you want to detect or count your potatoes, don't use this one. So getting to the next category, what this talk is actually all about, the multimodal LLMs, or the large multimodal models, the LMMs. Again, a quick architecture overview, not so in-depth, because actually not a lot of information is available for the architecture behind these models. And these models, I mean, the popular ones like GPT-4 Vision, Gemini Pro Vision, Claude 3, which was actually released 2 weeks ago. So a very recent model, but in general, same pattern. You feed in 2 input modalities. First one being what we now call a prompt. So it's not just a list of vocabulary anymore. It's an actual prompt that you feed in, of course, still your image. So in this case, what's happening in the image, a man and a woman are cross-country skiing with their dog. Simple example, but of course, that's a general idea of these models. So today I want to talk about these 3 models. So the first one being GPT-4 Vision from OpenAI, then Gemini 1 Pro Vision from Google or DeepMind, I know Gemini 1.5 has been released by now, which is supposed to be a lot better, but I did not manage to get access in time to include it in the talk. So when I talk about Gemini today, it's Gemini 1 V1, not the 1.5 version. And then finally, Claude 3 Sonnet, which is the model, as you can see, that was released 2 weeks ago. So very recent. To that one, I did manage to get access in time to include some examples and some learnings in the talk today. So this slide, so yeah, basically, as you can see, GPT-4 Vision is the oldest one of the models, but still it was released end of last year. So that's very recent, but I think in the AI space, everyone is used to rapid things evolving. In terms of parameters, it's a bit of a guessing game because none of them really like to release the amount of parameters that behind their models. So for some, there are some public guesses around. The most recent one I did not manage to find. I mean, people have been putting estimates online. Some say it's 70 billion, some say it's 2 trillion. So clearly there's a big range. So it's a lot of parameter. It's a large model. In terms of modalities, so both GPT-4 Vision and Gemini Pro Vision take in text, images, and video as input. You can directly use a video. You could say if you can feed in images, then you can feed in a video because a video is a bunch of images. But for Claude, there's no like direct feeding a video in. And currently there's a limit with the API to 20 images. So you couldn't really say that you can feed in videos, for example. And then the second to last one, the image size, that's actually quite interesting. Together with the image pricing, I think are the most interesting stats and what you should really look at to compare these two models. So for GPT-4 Vision, I mean, the max image size, it's always expressed as there's a max amount of input tokens. And even then, each of them has like a different way of defining your max input size. So it's a bit difficult to have a direct comparison, but roughly you can see the max input size in terms of pixels. And what's important is that Gemini Pro allows you to feed in the biggest images. And in the examples that I'll show, you'll see why that's actually important. Again, in terms of pricing, it's also difficult to compare because they all use different pricing schemes for images. For text, it's typically, okay, you pay this amount per million tokens or whatever. But for images, for some reason, they decide to all do it differently. So I just try to put in some numbers to give you a rough idea. But again, you could say that Gemini Pro is the cheaper one because they have just a fixed price per image, regardless of the resolution of your image, which is quite interesting. All right, a lot of numbers, but just as a bit of an overview to, again, set the scene how these models actually compare. Then next, what I basically want to do, Arne already mentioned it, at ML6 we're very practical. So instead of going to a lot of theoretical and technical details of these models, I just want to show you examples. These examples are just things that I thought of. What if I feed this into these models? What will I get as output? But also questions we've had from clients and also questions that we got from clients in the past, where I realized, okay, in the past we trained a custom machine learning model. We spent a lot of time gathering a data set, labeling data, where now just with this model, you can fix it. So I'm going to go through these examples and compare a bit how GPT-4 Vision, Gemini, and Claude compare to each other. So for this first one, there's these protein bars, just a food label that I put in. And I'm wondering, so this is an actual case that we had for a client. They want to extract all sorts of information. So I've limited it here. So I basically ask you my prompt, how much energy, salt, and fats are in this product per 100 grams. And for convenience, give me the result in a JSON format. And then, surprisingly, GPT-4 Vision is not able to help me, but it's interesting. It recognizes that it's not able to help me. So it gives me a response, but basically it boils down to, okay, I recognize that there's some text containing specific amounts, but the text is quite small, not entirely readable, so it cannot help me, which is interesting and also makes sense, again, if we look at the max image size I can feed as an input. So it's quite important if you feed in big images with small text, these models don't work. And even if you resize, you will lose maybe too much detail and it won't work. In this overview, we see, and already mentioned it, Gemini has a bigger max input size. So let's see, can Gemini deal with this type of input and this prompt? And yes, Gemini, there's no issue at all. It gives me a JSON with energy, salt, and fats per 100 grams, extracted it from the image, works quite well. It's not rocket science, but I do think it's quite interesting. It's not a classical OCR method where we just grab literal text from the label. There's some reasoning involved because it actually gives these quantities for 100 grams and 45 grams. And then it has to reason, okay, it's all next to each other. It's like, it's not in a table. So there's some reasoning, but okay, not the most complex case. But Gemini did the trick. And unfortunately, Claude was apparently also struggling with the image resolution, but as opposed to GPT-4 actually telling me text might be too small, cannot help you. Claude just said, I'll just give you random numbers and you figure it out. So basically every value that it gave me was wrong. So be aware. All right, so some information extraction from a document, from an image. Interesting, I thought, okay, let's go a step further and see how advanced are the reasoning capabilities of these models. Again, not rocket science, but it gets a bit more complex. I feed in this manual from a TV remote. It has some instructions on it, like how do you switch channels? How can you switch audio? If you want to go to this channel and this, you press first this button and that button. That's all in the image. So here my prompt is, how do I watch channel 54-3, which is a real channel, it's a special channel, apparently, with stereo audio. And again, looking at, can these models extract the information based on both the text, the image, the technical stuff in there? And in this case, yes, GPT-4 Vision. I've noticed from my experiments, and you'll probably also notice it with the examples that I will show, GPT-4 Vision is very, very talkative. Even if you ask it simple questions, it will give you like a whole response, a lot of stuff, and it will be accurate. The information you want will be in there, but it's sometimes a bit too much. So in this case, basically what I want is, I guess, just point 3 and 4, but it gives me more stuff. Make sure to turn on your TV. Okay, thank you, GPT-4 Vision, but it's accurate. It's a good response. Looking at Gemini Pro, Gemini not so talkative, but it is correct. It gives me the essence of the information I want from the image. It says, okay, press those buttons, press that button, then that button, finally press that button, done, and you have what you want. It's correct, it's just a lot shorter. And then to conclude, Claude 3, also correct, a bit in between, also gives a bit more text, some steps, but again, it's correct, gives you some steps what you can do. And you'll see like GPT-4 Vision and Claude, instead of just saying, this is how you do it, they really like to start with some introduction and then a bit of a conclusion always. It's like they give you a talk about how they solve your problem, but it's correct. All right, so 2 examples already, pretty decent results, I would say. Then I thought, okay, let's move to a bit of another industry, another context. So in this case, manufacturing, what happens a lot in manufacturing is, okay, we want to do quality control. So this, some random image I grabbed from the internet. We want to do quality control in the wood sector. So someone that's producing wooden planks for whatever reason. So the prompt is, in a manufacturing context, which defects are present in this image and how likely are they? Surprise, surprise, a lot of text from GPT-4 Vision, but again, it's correct, it's not wrong. It lists defects that actually happen quite common. We have a client in that industry, and these are indeed the types of stuff that they're looking for in terms of quality inspection. But that's interesting, knots, warping, rough sawing, variations in color and grain. It's all correct. And within the text, it does give some, like a sense of how likely it is present in the image that you've actually given. So correct response, was happy with the result. Gemini also was quite decent, gave a bit of a shorter list, warping, splitting, checking. Indeed, these are common defects, and in this case, they're all present. You can see like some cracks, you can see the wood being warped a little bit. So correct response, pretty nice. Finally, Claude 3 gave like quite a lot in the response. I mean, I've put some stuff in bold, but it's like chipped or flaking green paint, scratches, dings, discoloration, yeah, so paint on the coating, improper finishing, handling damage, environmental exposure, aging of the materials over time. So it felt a bit like it was hiding that it was not sure by just giving me a lot of stuff that could potentially be wrong. But if you really read through it, it's not wrong what it's saying. So it does some proper inspection of the image. So again, quite interesting. All right, another example, actually one that I added today to this slide deck because I got a question from someone from our sales team. Hey, someone's interested in doing this and they want to see if they have gathered a big enough data set. And my first response was, why do you still need a data set? Pretty sure that what you want to do, you can just do with a multimodal model. So what did this client want? Given images of cars, they wanted the car brand, the type, the body type, the amount of doors, and the color of the car. And again, I've included, give me the answer in JSON format for convenience. GPT-4 just aces it. It's a Toyota Corolla. It's a hatchback, 5-door, red. All correct, decent, works. No need to train them all. Pretty nice. Same story for Gemini Pro. Toyota Corolla, hatchback, 5-door, red. Works decent. And of course, I'm showing single images for these use cases. I've tested it on more, so it's not that I'm cherry picking. Of course, there will be examples where it maybe fails, but same applies to a custom model that you trained. And again, Claude 3 on it. Toyota Corolla, hatchback, 5-door, red. All correct. So pretty nice. All right. And then I thought I really have to find an image where all these models fail. And then I came across this on LinkedIn and I thought, okay, let's feed it to these models. These days, that's a bit of, that's a reflex that I think that I have to comment what happens if I feed it to these types of models. Who here knows this riddle, or who here that side now knows the answer to the riddle? Do not shout it yet, but just want to see who can solve it themselves. I leave some time. Raise your hand if you know the answer. See a couple of hands, but not a lot. It actually also took me quite some time to see if I could figure it out. All right, so it took me quite some time, but I wondered, GPT-4 Vision, can you do it? And I was actually quite surprised. GPT-4 Vision gave me, again, very long response, but a bit towards the end, it was very accurate. So actually, the riddle, so who of them was lying? It was Rick, because Rick is the only car that has snow below it. So clearly he left no snow, no snow, no snow. And GPT-4 picked up on that. So it only got the image, it read the riddle from the image, and then it actually started listing, okay, Alex's house shows a car with snow on top, as well as a snow-covered driveway and path, suggesting no recent movement. Same for the other houses. And then Rick, for some reason it says car with no snow on top. That's not really accurate, but we'll ignore that. But the driveway has not been shoveled, picks up on the correct cue, and is able to solve the riddle. Was quite impressed. But then, Gemini, just confident, short answer. Mariah is the thief. There's no footprints leading to her house. True, there's no footprints leading to her house, but yeah, just confidently, very confidently wrong. And then Claude 3. Again, Mariah, no idea why these models think that. I think the reason here, looking at the houses, yeah. So Mariah's house is the only one with a car visible in the driveway. Weird. Suggesting she was likely not at home when the theft occurred, making her the liar in the riddle and therefore the suspected thief. So just completely wrong, which is interesting. But if you look at it, or at least the assumptions, Claude, the Sonnet version, is the smallest model of them all. And I think this clearly shows it that it's failing the most. You could say that Gemini is better by keeping it short, but yeah, they're both wrong anyway. All right, so that were just a couple of examples of things I tried, things I saw from clients again. So quick takeaways, it's very short, but so the pros, it's capable of these types of models are capable of complex reasoning and visual understanding. I think the riddle at the end is a nice example of that. Some people solve the riddle, feed it in the model, wait a couple of seconds, and it's able to like figure it all out, which to me is pretty cool, but be aware of these downsides. So as we saw at the beginning, difficulty with small text, also spatial reasoning. For example, counting. If you feed in an image of coins on the floor and ask how many coins are there on the floor, most of these models will fail. They're really not great at those types of tasks. And then, yeah, the other one, hallucinations, like with the riddle at the end, just saying Mariah is the thief, or with the protein bar at the beginning, just confidently giving me random numbers that do not make sense at all. So it's really important if you use these models, be aware. So if you directly deploy this model to production for some use case, you will get nonsense or hallucinations at some point. So that's really important that you're aware of that. So when do you use these models? For complex multimodal reasoning, where a textual response is sufficient. I mentioned that again here, because if you have a use case where you need to localize something, so you need bounding boxes, this will not help you. Even if you ask these models, give me bounding box coordinates in a text response and then draw it, it's nonsense. Do not try it. I tried. And then I think the most important part of this sentence is with human supervision. So because of these hallucinations, you can use it as a sort of assistant for very complex tasks, but always have a human sort of in the loop to check the final response. You can probably save a lot of time for a lot of people having this as an assistant, but do not just deploy it in isolation and have no one check it because it will go wrong. All right, then a final shameless plug of a demo that we've built. You can go to the URL, so vision-demo.ml6.eu, or you can scan the QR code. What this demo is behind the scene is GPT-4 Vision, and basically you can upload any image you want, and we will do quality inspection on it. So in this case, so no other context, just feed in the image, and we will tell you, okay, this is what we see on the image. These are defects that can happen, and this one we think is likely on the image you've uploaded. And as you can see, you can put in like leaves, petri dishes with like bacterial colonies, the manufacturing context one, you can basically feed in everything. And so, for example, for the leaf, this is what our demo will give. So it will recognize this is a close-up of a tomato plant leaf with potential signs of disease or damage, which is quite impressive that it already picks that up. But then we list the potential defects that can happen and how likely they are. You can try it out yourself, but the response is accurate, at least for this example, of course, because hallucinations still happen even in our demo, unfortunately. So yeah, feel free to try it out yourself. So it's one of the examples that I've shown, experiment with it. And I hope it also sort of inspires you to figure out use cases where you can use these types of models, because they are impressive, but just be aware of the downsides. Then conclusion, because of course no talk without a conclusion. Two things I still wanted to mention, some cool developments going on. So it's a bit contradictory, but these large multimodal models, we're starting to see the tiny multimodal models, which is the tiny version of the large model. Bunny and Moon Dream are two of them. And these try to do the same. Of course, they're less accurate, but you can deploy these on like edge compute devices, which is quite nice if you don't have time to send stuff to the cloud, for example. So that's evolving, and those are getting a lot better. Then there's also, which to me are the most interesting ones, the grounding multimodal models. Grounding meaning they will give you a response and ground their response. What that means is, for example, in the riddle, it will say, I forgot who it was, I think Rick. Rick is the thief because of this and this and this reason, and it will draw a bounding box around, for example, the part under the car that has no snow. So it is able to give you bounding boxes to ground its response. If you ask how many apples are there, it will put bounding boxes around the apples and say there's 5 because there's bounding box 1, 2, 3, 4, 5. Very interesting models, but they need to improve a lot. And then on the other side is a bit my final take, my final conclusion. I think a lot of custom models will be replaced by LLMs. So the example with the red car is one of them. That's a case where an actual client is still training machine learning models on a data set. And this model can actually replace it. And there will be a lot more cases where this will happen. Yep, all right. And that was my final slide. So thanks for your attention, and I'll happily answer any questions.
Thank you. How do you evaluate multimodals? Like for LLMs with NLP, for example, we have LLM as a judge. Do you have LMMs as a judge?
Yeah, I anticipated that question. Perfect, thank you.
Okay.
So there are benchmarks on these types of multimodal things. So these are some examples. This image showcases, for example, how Claude 3 Opus, which is like the bigger version of Sonnet, is supposed to beat, for example, GPT-4 Vision on, I think, most of them. I steered clear of these benchmarks because these are numbers, and there's some data sets on some types of things, but to me, these numbers are not very practical. So that's why I feel like, okay, if you want to test out a use case, feed it into those models and see what the type of response is. But you can benchmark it. These things exist. When they release these models, there's benchmarks. You can compare them, but it's up to you to decide how useful these benchmarks are. Other questions for there?
2 questions. One is, which LLM have you used for the demo? Or
The demo is with GPT-4 Vision. I'm currently working on including Claude 3, but we're waiting for the best version, the Opus 1, to be released, because it's supposed to be better than GPT-4 Vision according to these benchmarks.
And second question, do you see any open source development on the horizon?
Yeah, so there are some open source versions. I think Lava is one of them. Today, I kind of looked at sort of the big ones from the big players, and because at this point, those are still the better ones. But I think as we saw with LLMs, also with the LMMs, the open source version are catching up. They're not there yet, but they're getting closer and closer and closer. So maybe in a couple of months, maybe in a year, we'll start to see them being equal to these models of the big players.
Okay, thank you.
Other questions right here?
So for object detection tasks, or like what you've shown us earlier, would you still use YOLO, or you would use, I don't know, multimodal?
Well, first of all, for object detection, you cannot use any of the models listed here because those are not capable of giving you bounding boxes. So your options are either the classical way, training a custom object detector on a data set, or use the open vocabulary one, like the YOLO World one. And I think there again, there are benchmarks, there are metrics, but test it out in your use case. If your use case is counting potatoes, I've saved you some time, do not use it. But yeah, you should test it out and see how they perform, because again, the benchmarks give a general idea, but you should really test it for yourself.
In the demo, I noticed that also the model output the likeness of the defects. Can you share the prompt or explain how you ask that?
I don't have the exact prompt here. That's also like the biggest clue behind the demo and what we spent the most time on. Like it's a joke. AI engineers are becoming prompt engineers, but for these types of models, it is more or less true. It's quite an extensive prompt, and it's also a lot of learnings that we've seen from other projects that we've done in terms of prompt engineering. Some things that are in there is, for example, in terms for the likelihood of a defect. We ask it, or what we did first is give us a score between 0 and 100. But then for some reason, it would always say like 70%. And then we tried, okay, 0 to 10, and still it did not make sense. And for example, for those types of things, the trick is for the range that you ask it to give a score in, for each number in the range, say what it means. So in the end, we went with give us a score from 0 to 5, 0 meaning this, 5 meaning this, 1 meaning this, 2 meaning this, and then it works really well. So it's like these types of nuances and tricks that you need to know in terms of prompt engineering, but I think there's also quite a lot of blog posts online, but I can say it's quite an extensive prompt that we used for the demo.
Just maybe a very short follow-up. So in the demo, there's no domain-specific knowledge that you're adding in. It's all GPT-4. Okay.
Yep. Yeah, it's GPT-4. No domain-specific knowledge, and it's impressive how it is capable of giving decent responses. We've put in images from the dental space, healthcare space. It knows like diseases that the average person has no clue that they even exist. It's quite impressive how good they transfer to all sorts of domains. So I really challenge you, find an image where it fails. Of course, something needs to be properly visible in the image if you feed him nonsense like garbage in, garbage out, of course. But yeah, so far I was always impressed. If you feed in a proper image, the response, it's always very good.
Yeah, just curious, why do you think the bounding box job failed? And the part of the question is, especially from the riddle case, it seems like at least GPT-4 has some awareness of the regions of the image and can base upon it, like some reasoning upon it, but however, the bounding box didn't work.
Yeah, that's an interesting question. And again, to repeat, so none of the models, so Gemini, GPT-4 Vision, and Claude, none of them can give you decent bounding boxes, at least not consistently. Again, it's a bit of guesswork why that is, because we don't have the details of the architecture. But I think, and it's a bit of a vague answer, they were simply not trained for spatial reasoning. It's really like, here is a general image, give me a text output. The way that those models were trained, at no point was the model required to pinpoint a location in an image. So during like the massive training that happened, it never had to do that. So if you then suddenly ask it something that it never had to do, then it will fail. I mean, there are cases where it gives you a bounding box that is roughly correct, but most of the times the bounding box that you get, so by asking it, give me coordinates in text, mostly it's just pure nonsense. But yeah, it's a bit of guesswork.
Hi, thank you for the talk. And one question, in the demo, were you using like multiple prompts or one bigger one? Or when do you recommend maybe to use multiple one because there are some pattern of limitation there?
Yeah, again, interesting question. For the demo is just a single prompt. We experimented with multiple ones. A single prompt did the trick, but we have other use cases that we are actually running in production for clients where we use a chain of sort of experts. So we call them agents, where each has a very specific task. So if your task gets a bit more complex, it really helps to split it up and then make sure that your LLM or multimodal model, whatever you use for each task, has an extensive prompt that really explains this is what you should do in your response, this should be the meaning, this is what I expect. And by allowing it to focus on each specific task and then putting them next to each other, you can do quite impressive stuff. But so the demo is just a single prompt.
Last question, maybe.
Thank you for the nice presentation. So I will circle back to the bounding box question and probably include more sophisticated computer vision tasks that could be potentially solved with such kind of networks, you know. So in the current networks, it's a sophisticated reasoning system combining the vision and the text prompts, right? So like as a computer vision engineer, what do you think that such models could be extended in multitask learning fashion for, you know, other vision tasks, given the fact that those organizations could access, you know, domain specific data and annotation from bigger players of, you know, computer vision problems. Like, I don't know, they could have data from Tesla or Waymo and train because the feature representation is really versatile. You could use it for many different tasks. So yeah, my question is, what's your take as a computer vision engineer that can this development be taking place in the future, or how do you take a look at this?
Yeah, so my take, I think it's a bit same to the previous question. It's all about having the data available. So getting these image pairs with text that we're trained on, it's relatively available and easy to get these days. And these big players, they have massive data sets. I mean, they basically, you could say, train on the entire internet. But they currently do not have these massive sets of like complicated prompts with images with bounding boxes. And I think as soon as you start to gather that and actually can train a model to do spatial reasoning, then we will have like the perfect mix of open world object detectors meets LLM meets multimodal. So to me, it's a matter of gathering the data and training it on a massive scale to be able to do it.
Thank you.
All right, let's maybe wrap up the questions here to save some time for networking. Thanks again, Jules.
Thanks.
All right, so we have about half an hour left before we get kicked out. So in the meantime, please enjoy the drinks and feel free to network a bit more. And thank you all for attending this night.